Hello students, let's learn about chirality of organic compounds due to presence of nitrogen. Introduction. A chiral carbon is similar to chiral center which is possessed by nitrogen because both of them have the same tetrahedral arrangement of electron pair, that is the central atom has sp3 hybrid, whether it is carbon atom or whether it is nitrogen. The only difference is that in nitrogen, they have a lone pair of electrons, that is the non-bonded electron pair, which is not participating in bond formation. So generally nitrogen has 3 substituent, whereas the carbon they have 4 substituent around them. But still, nitrogen having 3 substituent and a lone pair on it makes it a chiral atom. Now this kind of nitrogen wherein they have 3 substituents and 1 lone pair on them, though it makes it a chiral carbon, okay, they fall under a category of enantiomers which is called as invertomers. So let us understand what is invertomers. Definition: invertomers are isomers that can be interconverted by inversion of an atom that has a lone pair of electrons. Chiral amines have pyramidal geometry. However, a nitrogen atom with a pair of non-bonded electrons rapidly turns inside out at room temperature. This is called as amine inversion. So amine inversion also has another name called as umbrella inversion, and they are nothing but a pair of invertomers. So let us understand the invertomers and also the stereochemistry of them. So the diagram on the left and right, they are a pair of invertomers. So what is the meaning of an invertomer? So usually nitrogen, as we all just now studied that, they have a tetrahedral, geometry, and nitrogen is having the sp3 hybridized nitrogen, wherein the nitrogen is having 3 substituents and 1 lone pair on it. So now this is similar to an umbrella. So what happens when we use an umbrella? Okay, so umbrella is something like this, right? So this is a umbrella. Just imagine that a wind is blowing like in this direction, and then the umbrella turns outwards. Okay, so when it turns outwards, so this is just how the invertomers also work, or this is how the nitrogen with its lone pair possess this extra type of enantiomers which are called as invertomers. So here we see that on the left side, the nitrogen has a lone pair above it, whereas the other 3 groups or substituents are pyramidal, right? Now, the invertomers are in such a way such that the lone pair which is above now is placed below. So this is a invertomers. So these are a pair of invertomers. So here what is happening is the lone pair, now we see it is below. Okay, it's placed below the atom nitrogen, whereas the other 3 are still having the pyramidal. Other 3 substituents are still having the pyramidal shape. So this is what we call as invertomers. So this is nothing but also called as the amine inversion or umbrella inversion. And this can be seen in the chiral amines only when the nitrogen has a lone pair on it. That is, a lone pair on nitrogen is not involving, or it is not formed any bond with any other atom. Okay, that's what we call as the tetravalent nitrogen, which is, it has not formed the tetravalent nitrogen, but only the nitrogen is having 3 substituent around them and 1 lone pair is still available as it is, and it is non-bonding. It's not involved in any bond formation. So only in this structure of nitrogen, okay, that is also nothing but the chiral amine, only in this structure of the nitrogen, only we can see this phase or this type of the enantiomers, which is called as invertomers. Okay, so invertomers, again, the name is called as the umbrella inversion because of the understanding of the nitrogen similar to an umbrella, wherein the umbrella is, once the wind blows, right, the umbrella can take the outward position, which is like this. So this is this structure and this structure, nothing but the enantiomers, or you can call them as the invertomers. Okay, and the same thing we can take it up with these pair of the invertomers. Okay, now coming to the transition state. So these two are having the tetrahedral structure, that is the sp3 hybridized carbon. So each of these nitrogen on both of them, on both of the forms, they have the sp3 hybridized carbon. Okay, they have the sp3 hybridized carbon. But now what happens in the planar transition state? So in the planar transition state, the nitrogen is, sorry, in the transition state, the nitrogen has the planarity. They possess the planarity in such a way that the lone pair is now forming a p orbital. Okay, the lone pair on nitrogen has a p orbital, and the three other substituents, that is the methyl hydrogen and the ethyl groups, they are planar. So in general, we can say that during the inversion, okay, during the amine inversion, they take up a transition state which has a planarity in them, and then they go back, or they get inverted and they arise in the another form, which is nothing but called as an invertomers. So they're nothing but a pair of enantiomers, but they are not resolvable. Okay, they're not resolvable, but just that they are a pair of enantiomers, and they're called as invertomers. Now, why this name of invertomers and why they cannot be resolved is the main understanding is, we have learned that in conformational isomers, there is no bond broken, right? But that is, isomers can form, or they can be present in one form to another form continuously. They're just moving from one form to another form continuously. Okay, for example, if we take cyclohexane, they have chair, they have board, they have twist board. So they are undergoing this conformation that changes continuously. So that's why they become a conformational isomers, wherein the bonds cannot be broken. So this is the main definition for conformation isomers. So similarly, invertomers are also nothing but, so that is these two pair of the invertomers, enantiomers, are nothing but they are conformational isomers. Okay, they cannot be isolated. They cannot be formed as a pair of enantiomers. They cannot have an R or S configuration, because they are undergoing this change. They're continuously getting inverted from one form to another form. So that is why they are now called as conformational isomers. Okay. So now this is about the nitrogen which has a lone pair on them. Okay, now next let us learn about the nitrogen which is which forms a quaternary salt and also other types of the groups. So now in this example, there's an example of butanamine. So this is an example wherein we see here the chirality is nothing but, so this is an amine, right, because it has an amine group in this, but the chirality is possessed by the stereogenic carbonate. So though this is an amine, it's the butanamine, but the chirality in this structure, butanamine, is obtained by the stereogenic carbon. So in this example, what happens is, and here we see the S form. So this butanamine can be obtained as a pair of enantiomers, because in this we do not see the stereogenic nitrogen in them, but we are seeing a stereogenic carbon in them. Okay, and amine is present in this structure. That's a butanamine. So hence, this is a stereogenic carbon, and the chirality in this, that is the chirality is due to the presence of the stereogenic carbon, and they can be easily resolved into the two pairs of enantiomers which have the different configuration. So this is different from the examples that we learned previously. So here we see there's no inversion which is obtained here. So hence they can be easily resolvable. So this is one example of quaternary ammonium salts. So quaternary ammonium salts, what happens is, the lone pair on the nitrogen, usually, okay, that is which is non-bonded. Okay, now here it has formed a bond. So that's why the nitrogen now is bonded, is having 4 different bonds around itself, R1, R2, R3 and R4. Hence it possesses positive charge. So now it becomes a quaternary ammonium salt. Now in this quaternary ammonium salt, we see there's no lone pair in them, because it has got bonded with another substituent, R4. So these examples, okay, these are again the chiral amines, and these can be isolable. That is, they can be obtained as a pair of enantiomers which can be isolated easily. So whether you want the R form of it, or whether you want the S form of it, both can be isolated easily, because these do not undergo the inversion. Okay, there is no amine inversion or umbrella inversion which can be observed in this quaternary ammonium salt, because a lone pair has been taken up to form a bond with R4. So okay, so that is why these can form a pair of enantiomers. Okay, now, so these were all the types of the structure of amine which show the chirality in them. Now, how do we assign R and S configuration? So this is again similar. It is going to follow the CIP rule, wherein the highest priority is given to the group which is having the higher atomic number because they have the higher atomic weight. So here also let us take this, there's an example here. Again, the ammonia molecule or chiral amine, chiral nitrogen we can see here because we see all the different substituents around the nitrogen and lone pair also. So hence it is going to be a chiral amine. So it is a stereogenic center here. Okay, now let us assign the R and S configuration. So when we look at the CIP rule and the priority table, we can understand that whenever we have OPH, that is the OC6H5 group, they're always having the highest priority. So that's why we are giving them the first priority. Now the second priority goes to OCH3. There's a methoxy group here. But here, and then the next priority goes to the acid. So that is what I'm telling you is with respect to this example. But here when we see at that's the acid group, so you see there's 1, 2, 3, 4, 5, 6 carbon atoms which are bonded to the carboxylic acid. So that is why what happens is now the priority changes from methoxy to acid because the acid now is having like a phenyl group bonded to that, or what you say like an aliphatic C6H5 group, okay, which is bonded to the acid. So that is why now the priority changes and this acid group gets the second priority. Now the third priority is between the lone pair and the methoxy. Always to remember is that, students, whenever you're assigning RNS for amines, the nitrogen always gets the least priority. Just like how we used to assign hydrogen in a stereogenic carbon, whenever we were assigning RNS, the hydrogen used to get the least priority. That is, we would give it a numbering as 4. Similarly, in amines also, the lone pair always gets the least priority. Okay, now coming to the third position, it's the methoxy group. So now, it is going to move in this way. So 1 on the OPH, second group acid, third group methoxy, fourth group the lone pair. Okay, now hence it is going to be like 1, 2, 3, 4 clockwise movement. Hence it is going to, we are going to assign it as the R configuration. Similarly, let's take one more example. So here we see all the 3 substituents on the nitrogen look similar because they have a phenyl group on them. But however, the substituent, that is the ortho substituent, let's look at the ortho substituents on each of them. So here we have an acid. Okay, so that's why we are giving the first priority. Next, among these two, there is a methyl group. So that's why we are giving it the second priority. And this is just a phenyl, third. And lone pair always gets the fourth position. So it is 1, 2, 3, 4. Again, clockwise movement. And hence we are going to give it as the R. So when you get groups like this, which look very similar, okay, like maybe all the 3 groups of phenyl, all the 3 groups are amines, or all the 3 groups are similar like oxygens, then there also you have to look at the priority, which are the substituents which are attached to them. Okay, next let's take one more example. So it's an example of aziridine. So here what happens is we see there's a lone pair. So lone pair always gets the fourth position or the least priority. Then we have a chlorine. So halogens always get the first priority because they are placed on the right side of the periodic table, have the highest atomic number. Now coming to the second position comes to the methyl group, CH3. Now the third position comes to the methylene. So here there are hydrogens, okay, there are hydrogens here. So that's why the methylene gets the third position and methyl gets the second. So here don't get confused between second and third position. Second is for methyl because it has CH3, whereas the third position has only 2 hydrogens, okay. So that is why third position for the methylene group. And fourth for the lone pair. So it is like 1, 2, 3, 4. Again, it's moving in the clockwise. So hence we are going to assign it as the R configuration. Next, one more example. So again, an example here wherein the nitrogen is having a lone pair on it. So hence we give the lone pair the least priority 4. And now you see there is an oxygen. So oxygen gets first priority 1. And between phenyl and ethyl group, Okay, between phenyl and ethyl, phenyl gets the higher priority, so 2, and ethyl 3. So 1, 2, 3, 4. Again, it's going the clockwise direction, and hence R. Okay, so thank you very much, students.